Okay, I am going to talk about magnetism. Magnetism, which is the study of magnets. So magnets have been around, well, and magnetic phenomena, I guess you could say. Magnets have been around for a while. You know, people knew for a while that certain kind of rock, would sort of always try to point, towards the North Pole of the Earth, for example. So they called, that end of the rock that would try to point north the North Pole, and the other end that would try to point south, the South Pole. And then they would notice, that if you put two such rocks together, often the South Pole, one would try to touch the North Pole, the other, and so those two would attract. Maybe there'd be forces there pulling those together. On the other hand, if you had two, magnets, and you tried to push the North Poles of both magnets together, you would get repulsion. So they would, try to repel each other. And so, that was around for a while. And people noticed also that if you take a magnet and, there's a North Pole and South Pole, and you break it, you cut it there, then you would actually form another North and South Pole. So then you'd have two little magnets with North-South and North-South. So you could never separate a North and South Pole. You couldn't break it off and have a North Pole that you could carry away, and a South Pole you could carry somewhere else. So anyway, this has been around for a while, and people sort of, played with magnets, and they made compasses from magnets, and did all kinds of neat things. But nobody really saw how this impacted anything else until people developed electricity and electric current. And then somebody was noticing one day that magnets exerted a force on electric wires. So, or sorry, not electric wires, but wires carrying electric current. So let me erase all this crap, and there we go, good enough. And so they found this was kind of interesting. So I'm going to draw an XYZ coordinate system here. Let's see. So let me do it like, I'm going to do it like this. There's my Y going up there. Here's my X, and then Z is vertical. So this is like pointing away from you, if you will. People found that if you have a wire, say, I'll make my wire, I don't know, let's just say we have a purple wire. You have a wire, and the wire is, purple, and it's carrying a current. So the current is going that way, right? We'll call capital I our current going through this wire. You could identify something called the magnetic field. The magnetic field is a vector field. It's like the electric field in that it's got a different value everywhere. It points somewhere and has a magnitude, but it behaves differently. So the magnetic field is typically denoted by a B. So let's say our magnetic field there was like that, B. And so the magnetic field, and if you ever put iron filings around a magnet, you've probably seen how you probably did this experiment in some previous science class in 3rd grade or whatever, where you would sort of see the iron filings turn and sort of form into lines that would curve around the magnet like that. And then you've seen pictures of the Earth where, here's the Earth, and there's my horrible North America, and there's South America, and Hawaii, and Alaska, and Europe, and here's Paris Hilton. And then, you probably know that there are magnetic field lines around the Earth. So magnets have these sort of lines of force, very similar to electric field lines, and we'll get to those in more detail. But those point in the direction of the magnetic field locally. So you have this magnetic field here. You have a wire carrying some current. And so what people found was that when you have a wire carrying current through a magnetic field, there is a force exerted on it. And there's a force, they call a magnetic force. So the force exerted by a magnetic field on a wire, on a current carrying wire, by magnetic field on a current carrying wire, carrying, you guys know how to spell carrying, I assume. If you are looking for me to help you with spelling the word carrying, you're probably in the wrong place. The force exerted by a magnetic field on a current carrying wire. So what they noticed about it was that it, first of all, is proportional to the current. That's not really surprising. So you have a stronger current, you have a stronger force. They found that the force was proportional to length of the wire. Also not very surprising. So, you know, the longer your wire, the bigger the total force on it. But that just really means the force per unit length is a constant. Not a big deal. Okay, proportional to the magnitude of the magnetic field. So I'm going to just write magnitude of your magnetic field B. And by the way, if you're wondering why the letter B is used for magnetic field, I have absolutely no idea. Sorry. Okay, so it's proportional to magnetic field B for, and now here's where it starts getting weird. These are all fairly, you know, obvious. Here's where it starts getting weird. It is proportional to the sine of the angle between the magnetic field and the current direction. So what that means is the current is going through the wire. Let's say it's, you know, it's going this way. The magnetic field points this way. This angle theta. The magnetic field is proportional to the sine of theta. So when the magnetic field and the current were pointing in the same direction, the sine was 0, and so there was actually no force on the wire when it was pointing along the magnetic field. But as soon as you turned it sideways and had the current flowing, you know, across the magnetic field, suddenly you get a force. And then here's the other weird thing. The force was also perpendicular to both the magnetic field and the current direction. So you would have this magnetic field going this way, and you have the current going this way, and the force would actually be acting perpendicular to both of those. So let me see if I can, I believe, if I remember this correctly, the force would actually, in this picture, say this is the plane, and you know, you can't really tell which direction I intend the magnetic field to be going here, so I'm just sort of going to draw some things and some right angles and hope you understand it. The force from the magnetic field would be going that way, where it's at a right angle to the current direction, and it's at, see, this is already going badly, and it's at a right angle to the magnetic field. So imagine there's sort of this plane here where B is the magnetic field, is in the plane, and the wire's in the plane. Then the force from the magnetic field is actually perpendicular to both the wire and to the magnetic field. Weird, weird, weird. So what we're going to need to do to express this mathematically is develop an operation, a vector operation, that is new to us. You may have seen it before, but it's new for this class, called the cross product. And that is what I'm going to do in my next video. So this is going to be proportional to the strength of the current, to the length of the wire, to the magnetic field, and then it's going to be perpendicular to both the field and the wire in the current direction, and it's going to depend on this angle between, or the sine of this angle between the magnetic field and the current direction. Weird, weird, wild stuff. So we will get to that in the next video.